First thing I want to bring up is that a couple of people asked me to discuss, rather than using the tables to find areas in the normal distribution, to use Excel instead. Excel, as you already know, Excel has many statistical functions built into it already. Okay. But when we're talking about normal distribution, calculating confidence intervals, calculating probabilities for selecting an individual in a population, and so on and so forth, the main ones that we're interested in is the ones that calculate the normal distribution, the percentage of the area of the normal distribution that's represented by a certain value or a z-score, and going the other direction. If we know what the probability is of the area that we want in the distribution, what is a z-score that represents that? Okay, so to start off with, let's start off with the functions called norm s dist and norm s inverse. Okay, I'm going to type in here, and Excel's going to help you out with this. I'm going to type in here equals norm s dist. Okay, hit parentheses. And when I hit parentheses, what comes up is z, right? So it's asking you for a z-score. So if you have a z-score of negative 1, let's say, and we know that -1, because of the empirical rule, -1 is going to represent an area to the left of that, which is going to be, well, let's see, 68% in the middle, 34% between 50 and -1. So it's going to be around 16%, right? If you visualize that normal distribution. So I'm going to put 1 in here for z. And hit enter. And it gives me, oops, what did I just do wrong? I just said I said -1, right? So in fact, if I go back in there and change that to -1, I get my roughly 16%. Okay, when I put +1 in there, I got 84%. Why did I get 84%? Because a z-score of +1 is to the right of the mean, and it represents the point, the z-score, where 84% of the population is below that, right? So you can put in any z-score you want. Like, for instance, if you calculate a z-score is equal to, let's say, 1.23, hit enter. Instead of going to the table, you can use Excel to tell you that the area to the left of that point is about 89% or 0.89. If I were to use the z-table, and I think I got one open, I have one up here. I lost it somewhere. Okay, I'll pull one up. Okay, where is it? There it is. If I were to use the z-table, where'd it go? Yeah, that's not what I want. I have it now. Nope, still don't have it. I know it's there, back there. There it is. If I were going to look up positive 1.25 for z-score, it's going to be, and remember, it represents the z-score. It's going to represent the area to the left of it, the shaded area, in other words, for that z-score. So plus 1.25, 1.20, 1, 2, 3, 4, 5, and that's it, positive 1.025, and it's 89.44. The 80, same as we got with using norm s dist. Yes.
Can you find z-values on Excel as well?
Yes, you can. Okay, what do you think we might use for that? Yeah, let's give it a try. Okay, test my memory of it here. Okay, equal t dist, parentheses, and now it's at, whoop, hang on a second now. T dist, t test, t inverse, t dist. Okay, now the only thing is the t distribution is going to be based on the sample size, right? So in other words, the t value that you're going to get is going to be dependent on what your sample size is. So in other words, where the z value, where the z-score doesn't, that, it assumes that you know the standard deviation and you don't care what the sample size is, or it's a very large sample size, or you know the population standard deviation. The t is going to be different depending on what the sample size is. So this time, when I hit put in t dist in parentheses, it's asking me for x, the value that I'm interested in, the number of degrees of freedom, and the number of tails, two-tailed or one-tailed. Okay, it's always generally going to be two-tailed. So I'm going to say the value is, let's see, what am I looking for here? I'm going to look for, what's that? Oops, okay, hang on a second here. Let me think about x here. Okay, say 1.9, 2, comma, I'm going to say a sample size of 10, which is 9 degrees of freedom, and two tail. Okay, and interestingly enough, we're maybe more interested in T inverse than we are in T dist. Hang on a second. Okay, I think I'm more interested in T inverse because we want a T number to use for confidence interval for T. So what confidence interval do you want to use for the T distribution? You want 95%? Okay, use 95%. Okay, so it's asking me for probability and degrees of freedom. So probability and degrees of freedom. So I'm going to put in here the probability is going to be, say, 0.95. Parentheses, the degrees of freedom is going to be, let's pick a sample size. Sample size of 20 would be 19 degrees of freedom. Okay, everybody knows that the degrees of freedom is the sample size minus 1. That's not what I want. Oops. Okay, I see the error. Okay. I have to check this now because I don't remember for sure. I'm going to do this again. So 95% confidence interval, the degrees of, with 20, sample size of 20, the area that's out, that we're interested in, 95% confidence interval, we're talking about having a 5% chance of being incorrect, missing the mean. So since it's going to be two-tailed, we're going to use 2.5% as our probability of being wrong. So I'm going to go in here and say equals T inverse, parentheses, and we're going to have to check this when I get this done, 0.025, comma, and then I'm going to put in the degrees of freedom, which are 19, and this should give me my t-score, what my t should be. And it gives me a t of 2.433. Now, I'm not sure about that. It might have been that I should have put it in as two-sided, in other words, 5%. So the way I'm going to test it is I'm going to go to the t-table and check to see what it really should be. I'm going to do it the other way too. Equals t inverse, parentheses, 0.05, comma, and 19 degrees of freedom. That time I got 2.09. I think that's going to be right. So let's get the t-table. Okay, press the t-table. And you can use it from any text that you want. Your text, I happen to like using this one from another textbook that we use frequently. Let's see. Here's a t-table. And for 19 degrees of freedom, here's 19 degrees of freedom. I'm looking for a 95% confidence interval, or 2.5% in each tail. And that's going to be in this column here. So 19 is going to be 2.09. So the right choice would have been to put 5% in there. Okay, let's do another example, for instance, okay, for determining what the t-score has to be. Let's say we want to do a 90% confidence interval, right? That would be 10% chance of being wrong, right? And we want a sample size of 10. So I'm going to put in here equals t inverse, parentheses, 10%, comma, and 9 degrees of freedom. Okay, this is going to be bigger because it's a smaller sample size. Okay, I lost it there. Okay, hit enter. And it's going to be, actually, it's going to be bigger than it would have been if it would have been 95%. It's 1.83. I think you actually did that on one of the examples in the lecture. Okay, so you could either use the table to look up 9 degrees of freedom, right here, for a 90% confidence interval, and it's 1.833, or you could use Excel to get that same number. Okay. So I got a little bit off base there. I wasn't expecting to do that. You kind of threw a curve at me there, so I stumbled a little bit on that, but that's the way you would use that. But as far as a normal distribution, norm as dist would ask you to put in other words, it would ask you to put in the z-score that you want and give you the probability. That's, in other words, the area to the normal distribution to the left of that. If you put in norm S inverse, it asks you to put in the p-value, and it gives you the equivalent z-score for that, for normal distribution. Now, there's also norm dist and norm inverse. I'm going to put that in here now. Equals norm dist, parentheses. What's it ask for now? Well, now it asks for x, like mean, standard deviation, and cumulative. What's it looking for there? Well, in that case, it's not asking you for the z-score. It's asking you for the value that you're interested in. So, for instance, let's say we have a population of men from 40 to 60 years old, and the mean for the mean blood pressure for that population is 100, and the standard deviation for that population is, let's say, 10. Right? And we want to know what's the probability of picking an individual from that population who has a blood pressure less than 85. So our X is 85, our mean is 100, our standard deviation is 10, and cumulative is always going to be yes, because it's always going to give us the area down from that point. So I'm going to put that in for here. So 85, X, 100. Our standard deviation was 10, and cumulative is going to be true. Okay, I'm going to hit enter, and it gives me an area of 6%. So 6% of the population has a blood pressure below 8. It saved you a step. You didn't have to calculate the z-score first and then use norm S-dist. See, that's the difference between norm dist and norm S-dist. The S stands for the standard normal distribution, where you give it a z-score and it gives you a p-value, or you give it a p-value, give you a z-score. Norm dist and norm inverse will give you the whole ball of wax. You can put in all of that, all of your values, and skip the calculation of the z-score. I'll put this list on Blackboard so you guys can play around with it. It's actually an Excel spreadsheet, so you can actually type into it and play around. It actually might even be there in one of the previous lectures, one of the previous labs. Okay, so that's the way you would do that. That's how you would use Excel to calculate the values that are in the T table or in the Z table, so you can skip going to the table if you don't have the tables handy and so on. Okay, it's even a little bit more, probably a little bit more precise as well. Okay, so let's go to the exercises that are posted on Blackboard, but maybe we can work together on those. Okay, I'm going to go here, and that's going to be lab exercise for session 7. Session 7 lab exercise. Blow it up a little bit more. Okay, and for this, again, it says up there you can use Excel, you can use the Z table, you can use a T table, and so on and so forth. Okay, so what are we doing here? First thing, let's discuss how we're going to handle this. Nope, I shouldn't be communicating here. Well, let me try to get this in here. Okay. Okay. So what we're going to be looking at here is, in terms of calculating confidence intervals, is that we're going to be looking at a situation where we're taking repeated samples, right? We're always going to be working with samples. Can you see that behind me? Oh, my goodness. Went to sleep, maybe? What happened? That's interesting. That's a new one. There it goes. Get back again. Okay. We're taking repeated samples from a population. Okay, and that's those samples. Those samples can have, they all have a uniform size of n. We're going to wind up with from each one of them, we're going to wind up with a mean x bar, and we're also going to wind up with each one of them is going to have a standard deviation. But for the time being, we're going to assume that we know the population standard deviation. Okay, so when we take these repeated samples, I'm going to say, for instance, we're going to take 25 samples from a population. When we take those samples, we're going to wind up with a new distribution of those 25 numbers, right? And we're going to look at that. We're going to say to ourselves, well, since these are random samples from a roughly normally distributed population, we're going to say, well, they're going to be normally distributed also. In fact, even if the original population weren't completely normally distributed, the distribution of the samples from that population are going to be either normally distributed or closer to normally distributed than even the population is. So the mean, I would expect the mean x bar to approximate the population standard deviation. So if I told you that we took these 25 samples and we took the mean of each of those 25 samples, then I would expect that x bar is going to approximate the mean. And let's say in our particular case, that's equal to 80. Right, so x bar is equal to 80. Okay, so if I do this over and over and over and over again, the distribution of these samples, in other words, sometimes I may get 82, sometimes I may get 79, sometimes I may get 75. The distribution of these will be normal, each one of these sample results. So in other words, it's going to be likely that the results are going to be close to 80 each time I take a sample of 25 and take the average from that population. And it's going to be likely that they're going to be close to that, maybe 78, maybe 75, and so on as maybe 83 or something like that. But then occasionally I'll get an average that's further away, maybe 72, maybe 80, 86, and so on and so forth. But that's going to occur less frequently than the averages that are close to the population mean. And then as I get further and further away, the probability of getting a sample mean that's that far from the population mean is less and less likely. So that's why we wind up with a bell-shaped curve. Now, we know that the average for these samples, repeated samples, is going to approximate the population mean, but the standard deviation of the population, that represents the spread of everybody's, whatever this is like blood pressure, let's say. That's the spread of everyone's blood pressure, which could be very wide. Could be anywhere from 55 to 200, let's say. Right? It could be a very large spread. On the other hand, if we take a sample of size 25 from all of those people, then most of the time we'll get something close to the average for the population. Okay? So the spread for our samples is going to be different than sigma. It's not going to be the same as sigma, like the way x bar is going to be an estimate of mu. Sigma is going to give us some insight into the sample distribution, but it's not going to give us the same spread. Actually, the spread that we're looking for, the sample mean spread, is equal to sigma over the square root of the sample size. But what does that tell us? That tells us that the bigger the sample size is, the smaller that the standard deviation for this spread of samples is. So in other words, we would expect a narrower range of results for samples that have a large size. So since we're working with standard deviations and sigma and so on and so forth, I'm going to give this a new name and call it standard error. So basically what this is telling us is if I know the population standard deviation, right, I can predict the spread of repeated samples from that population that have the same size. So if I can predict the standard error, I can predict what the range of sample results that I would expect to get. For instance, I could apply the empirical rule and say that 95% of the time I would expect to get a sample mean X bar that's within 2 standard deviations of the population mean. Right? And if we have a larger sample size, well, then my sample mean is going to be narrower. My sample means are going to be narrower. My standard error is going to be a smaller number. So I have an even narrower range within which I can get 95% of the samples when I take it from the same population. Okay, so since I know that, I can now use that to predict not just what my mean is, but how likely it is that I'm close to my mean, how precisely I know my mean. So we know that that's where our confidence interval comes in. It's not going to let me do this. So I thoroughly confused you there. It's a lot simpler in action than it is in description. Questions about that to start? Yes.
Is it fair to say if this were an analogy on GRE, that mu is to X bar as sigma is to standard error? Mu is to X bar as sigma is to standard error.
Not quite. X bar is an approximation of mu. In other words, they'd be the same number. The standard error is going to be a smaller number than sigma because it's based on you're dividing by square root of the sample size.
Okay.
So standard deviation of your results are going to be narrower. So the bigger sample, the narrower is your band of certainty.
Okay.
For the
X
mean.
bar is always
Okay. Okay. So let's do an example here. So let's say that let's say I take a sample from from a population, and that's going to be, let's say that's 64 people that I sampled. Now I know that this population has a standard deviation of let's call it 8. Okay, and I'm going to say, and normally we really don't know that. Okay, and we're going to ignore the fact that we normally don't know that until we start doing problems that involve the t-test, the t-value. Okay, because the reason why we're going to use the t-value is because most of the time we can't use z because we really don't actually know the standard deviation. We're going to see why that's true. Okay, so let's say that I take a sample, 64, I randomly sample 64 people. The important thing, it's an independent sample, and we randomly sample, and I find that X bar is equal to let's say 70. Okay, so now I want to know, well, I took a sample of size 64. I know the population standard deviation is 8. What's the variability that I would get in repeatedly taking samples of that size? And that variability is going to be the standard error. The standard error is equal to sigma over the square root of the sample size. Right? So what's that? That's 8. I'm sorry? What was the 1? Oh, it's 1. Okay, yeah. Okay, you got ahead of me. 8 over 8 is equal to 1. Okay, so what does that tell me? That tells me that the distribution of samples around the true population mean is, if I take repeated samples of size 64, is going to be 1. Okay, so that I can use that to say, well, I think that this approximates the population mean, but I'm going to actually now use this, what I know about the standard error. I'm going to use that to help me understand how precisely I know this. Okay, so I'm going to call what I'm going to do is a confidence interval. And the confidence interval is going to be equal to my point estimate, which is X bar, okay, which is just the middle, right? If it were a proportion, I would call the proportion my point value. In other words, if I sampled 500 people and 100 of them had diabetes, I would say my proportion or my point estimate is 20%. Okay, so X bar, and I'm going to say that 95% of the time I'll be within 2 standard deviations of the population mean, 2 standard errors of the population mean. So I'm going to say X bar plus or minus 2 standard deviations times the standard error. Now, I use 2 because I just in my head, I know that when I use the empirical formula, that 95% of the results are within 2 standard deviations. But we know, we've talked about this before, we know that the real value there that represents 95% is 1.96 standard deviations below the mean and 1.96 standard deviations above the mean. So I'm going to use that instead now, instead of the 2 at this stage. So if I substitute that, I'm going to have 70 plus or minus 1.96 times my standard error, which is 1. So 70 minus this is going to be 69.04. I'm sorry, 68.04. And 70 plus that is going to be 71.96. So what am I saying here? I'm saying that I'm 95% confident that the true population mean is between these two numbers. Am I positive it is? No, I'm not, only 95% positive. So what does that mean? It means that if I do this 20 times, I'm going to be wrong 5 times. The population will be either less than 68 or more than 72. Okay? But at least I have some idea how precisely I know the true population. I have some way to understand what this prediction means. Now, let's take a look at what would have happened if the sample size were bigger. Okay, let's say that the sample size, instead of being 64, the sample size is, let's see, 144. Okay, what would that mean? Well, the standard error then would be equal to 8 over 12, right, is equal to 0.67. Okay, 0.66, whatever, right? So, am I right about that? No, nobody can contradict me there, right? Okay, so square root of 144 is 12. Okay, so now what's going to happen now? Well, it's going to be 70 plus or minus 1.96 times 0.67, right? Well, since the standard error is smaller, my sample size is bigger, my standard error is smaller, my confidence interval is going to be narrower. It's still a 95% confidence interval, but now it's a narrower range of numbers because of the sample size. Okay, so I'm going to, let's see what that might be. Yeah, I'll take your word for it. How much was that? 1.31? Okay. So, and again, you just mentioned something interesting. This number that I'm adding and subtracting here, that I'm adding and subtracting here, that's the margin of error. When you put the standard error and the z value that we're using together, you call that standard, the margin of error, which kind of makes intuitive sense. So that's going to be 68.69 to 71.31. Okay, it's a narrower range. Still 95% confident. Okay, so now let's throw another twist in here. What if I want to be 99% confident? Right? Well, I can't. 1.96 is a z-score that if you go that distance on either side of the mean, you have 95% of the values, 5% chance of being outside of that. What if I want to be 99% certain? Anybody remember what that z-score has to be? 2.58, right? Okay, as a matter of fact, just to make sure, okay, let's just to make sure, okay, equals norm, S inverse, parentheses, probability, and the probability is going to be, what did I say, was 99, so 0.01, parentheses, oh, I'm sorry, it should have been 0.05, right, 0.005, 5%, so it's going to be 0.5% on one side, 0.5% on the other, so it's 5% is 2.58, right, okay, so it comes up the same way. If you use a z-table, you get the same thing. Okay, so that's going to be 2.58. So how is that going to affect this? If I want to have a 99% confidence interval, I'm going to be working down at the bottom here. I know it's kind of hard for you guys to see. I'll do it over here. 95% confidence interval, I'm going to say x bar plus or minus, instead of 1.96, 2.58 times my standard error. I'm going to go back to a sample size of 64, make it simple. 1. Okay, so it's going to be 70 plus or minus 2.58. Okay, and I'll leave you guys to do the math on that for the minus and the plus. Okay, that's simple. Anybody know what you would use as z-score for a 90% confidence interval? This time I'll use the table. For a 90% confidence interval, whoops. Hang on a second. 90% means it's 5% on the lower end, 5% on the upper end. So I'm going to look at the lower end here and look for where I have, what's z-score I need to have 5% to the left of it. 0.05, 0.005. Here's 5.26. Let's see, 0.09. That's that one. See, where is it? It looks like it's right around here, right between these two numbers. I'll pick this one out here. So what is that? That's negative 1.64. Okay, right? 1.64 would be the z-score. 90% confidence interval, 1.64. 95% confidence interval, 1.96. And a 99% confidence interval, 2.58. Okay. T-scores can always vary, but that's always going to be the same. If you know the population standard deviation, or if you're working with a very large sample, we'll discuss why that works that way. You can use those three numbers for the confidence interval. And that's really all you need. Okay. So, just quickly, given the same sample size, right? Given the same sample size, which is wider, 90% confidence interval or 95% confidence interval? 90. Let's think about this. Which is wider, 90% or 95%? Wider. Which one is it? Which one is, are you less, which one are you're allowing yourself to have less confidence in? 90%, right? 90% confidence interval is wider, right? Why is it wider? Because you need it to be wider because you want to be, I'm sorry, I'm wrong. The 90% confidence interval is narrower because you're willing to accept more chance of being wrong. The 95% confidence is wider because you need it to be wider so you have a higher confidence that you've captured the mean. And the 99% confidence is the widest of all because you want to be as certain as you can be that you captured the mean. And what makes it wider? The only difference, if you take same sample size, the only difference is 1.64 times the standard error, 1.96 times the standard error, and 2.58 times the standard error. That z-score is what makes the confidence interval wider for the higher confidence intervals. Okay? Okay, good. Let's do a couple of examples here. Okay, let's go back to this. Okay, samples. You take sample size from a population of 100. It has a mean of 160. Assuming that the population is normally distributed with a standard deviation of sigma is equal to 30, compute a 95% confidence interval for the mean of the population. I'll give you guys a chance to give that a try. Mean is 100. The mean x bar is 160. Sigma is 30, and the sample size is 100. Shouldn't take you too long. Oops. What did I say? Sigma was 30, I think. Okay.
Okay.
I'll start working on it with you guys. Okay, so let's take a look at this. So sigma is equal to 30. We know that sample populations from the population. Sample size is 10, so the standard error of repeated samples is going to be 30 divided by the square root of 100. It's going to be equal to, that's 10, is going to be equal to 3. So now to calculate my confidence interval, what do we say, 95% confidence interval, I presume? Right, 95% confidence interval. Okay, it's going to be my point estimate, x bar, plus or minus, for 95%, it's going to be 1.96 times my standard error. Okay, so that's going to be 160 plus or minus 1.96 times 3. Okay, I'm going to just round that to 2 for our purposes right now. So it's 160 plus or minus, actually, why not just go ahead and do it? So that's going to be 0.12 less than 6. What's that? 5.88. So it's going to be 154.12 and 165.88. Okay, everybody get that? Okay, what would be different if I asked for a 90% confidence interval? What would be the only thing different here?
1.9.
Right, instead of using 1.96, we would use 1.64. And if we're 99% confidence interval, instead of using either one of those things, we would use 2.58. Okay, and as a consequence, a 90% confidence interval would be narrower because it's a smaller number that I'm adding and subtracting, right? Which means that I get a narrower range, but I'm not as confident that I really caught the mean. And if it were 2.58, it would be a wider range, and I would be more confident that I would be more confident, 99% confident, that I actually captured the true mean in between those two. Okay, let's take a look at the next part. Okay, so this is kind of the next part is kind of a twist. If the population were known to be 160, what would be the probability that a single observation selected at random from the population would have a value of less than 154? We just went a little bit backwards here, right? We went backwards in the sense that now I'm talking about a population. So when I'm talking about a population, the standard error goes out the window, right? Because I'm talking about one individual chosen at random from a population where I know the population mean, I know the population standard deviation. So what I'm looking at there is calculating a z-score, right? So let's take this. So that's kind of a detour from what we were doing up to this point. So let's see. Mu is equal to 160. Sigma is equal to 30. And x, the value I'm interested in, is 154. So how many standard deviations below the mean is 154? Well, z is equal to 154 minus 160 over 30 is equal to, let's see, 6 over 30, right? Which is equal to, what is that, 0.05? Yeah, minus, yeah. Minus 6 over 30 is equal to 1/5, right? Is negative 0.2, right? So the z-score is negative 0.2. Now I want the probability being more than that or less than that? Anybody remember? Probability would be less than that value. So I want the area to the left of that. So there's a couple of ways I could do that. One way is to go to my table, my z table, and look up negative 0.2, and 42% of the distribution is to the left of it. The probability of picking a person that has a value of 154 or less is 54, with 42%. Could I do that with Excel? Sure, I could. Right. So Excel, I could look up the z-score. I could use norm s dist, right? It equals norm s dist, parentheses, and tell it that the z-score is negative 0.2, and it gives me the area of 42%. I could also use norm dist equals norm dist, parentheses, and this time it asks me for what's x. X is 154. What is the mean? 160. What is the standard deviation? 30. What is a cumulative? True, always true, because you want the area to the left. And it gives me the same thing as well. So that one I could skip bypass, calculating the z-score. Okay, so let's go back to samples again, since we took a little bit of detour there. Okay. I'm going to skip that part. Okay. Let's go to number 2. After observing 25 randomly selected caseworkers, supervisor noticed the average number of cases carried by each worker in a week was 50. From previous long-term observations, known that the standard deviation for the entire department is 9 cases per week. Well, what is that doing? It's kind of like going an end round and telling you that the standard deviation is not for all of the caseworkers is 9. Okay, for the 25 people she sampled, the average number of cases that they carried was 50, with a population standard deviation of 9. Calculated 95% confidence interval for the mean number of cases per worker per week for the entire department. Okay, so and then a 90% and a 99%. Okay, so how are we going to do that? Let's get our piece of paper here. No, well, we know the population standard deviation. As long as you know the population standard deviation, you can use the z-score, right? Because you understand the distribution of repeated samples. If you don't know the population standard deviation, you don't know how samples are going to be distributed. That's a problem. We're going to deal with that problem shortly. Okay. So what did I say here? I said that the sample size is 50. I said that the mean, the sample size was how much? Anybody remember? 25. Okay. Yep, 25. The mean of our sample was 50, and our standard deviation for all the caseworkers for the entire population is 9. So if I want to calculate a 95% confidence interval, what am I going to use? I'm going to use X bar plus or minus 1.96 times my standard error, which I have yet to calculate. So my standard error is going to be equal to sigma over the square root of the sample size, which is going to be equal to 9 divided by sample size is 25. 5 is equal to 1.8, right? Yes, 1.8. Odd number. Did I get that right? Yes, I got that right. Okay. So standard error is equal to 1.8. So now substituting in here, right? So 50 plus or minus 1.96 times 1.8. Okay, so what's the average? What's our 95% confidence interval for the average number of cases carried by all the caseworkers in this population? Well, it's going to be 50 minus 1.96 times 1.8, which is, I'm so glad when you get ahead of me on this stuff. 3 point what? Okay, let's call it 5.3. Okay, so it's going to be 50 minus 3.58, which is 46.47, and 53.53. That's our 95% confidence interval. Everybody get that? Everyone got that same answer, right? Okay. How do I calculate my 99% confidence interval? There you go. Let's do it. 50 plus or minus 2.58 times 1.8, right? So our margin of error changes now, right? It gets bigger because I'm using 2.58 now. So our margin of error now is how much? 4.64, let's call it, okay? So, see, and it's bigger than that 3.53. So now it's going to be 50 minus that, which is going to be 45.36 to 54.64. It's a wider range. Since it's wider, we're more confident. We're 99% confident instead of 95% confident. I hate when everybody brings that up. The answer to that question is, in statistics, you don't round at all. If you're using Excel, a calculator, you store your numbers, you keep doing it. The reason why you don't round it all until the very end is because there are things that we do in statistics that may amplify the error. For instance, if I take 5.5 and I round it to 6, 5.6 and round it to 6, that's a certain that's whatever, but that's like 5. That's 10% error that I've added, right? But if I square, if at some point in the process I have to square that number, now when I square 5.5 and I square 6, I get a much bigger difference. So as you go along through your calculations, you can enlarge your error by rounding. So you don't want to round until you get to the very end. When you get to the very end, then technically you should be working with significant digits. What does that mean? Significant digits means, like, for instance, if I use 1.96 for my z-score, right? Really, it might actually be, if I really looked it up, might be really 1.96090113, whatever, right? If I use 1.96, I'm only using that number to 3 significant digits. So if I know my standard error is, I calculate my standard error, and my standard error is 3.5379476632, right? Maybe 8 digits or something like that. If I multiply 1.96 times another number, which is like 8 digits, and I get an answer, I have whatever number digits, 8, 10, 12 digits, I really only know the answer to 3 digits of precision, the lowest number of significant digits of the numbers I used in the calculations. Make sense? Right? So, in other words, the least precise number that you know in the calculation is what determines how close you are to your real answer, how much you can round. So technically at the end, like in this situation, I might round to 45.4. Okay? However, that's because I'm more of an industrial hygienist and, a chemist and a physicist than I am a statistician, right? On the exams, on the homeworks, most of the time we'll tell you to calculate it, and we'll give you an example. XX.XX, right? Ask you for 2 decimal places or something like that. We won't leave you hanging in the wind. Technically, you should figure it out based on the significant digits, right? So in other words, if I had used the empirical formula, which was, just a 2, right? Really, 2 really is not very precise at all. So, that's why the empirical formula really is just an estimate, right? Really, it's 2.0, you could probably call it, but that's only 2 digits, right? And so you would round to 2 digits or something like that, like 16% instead of 16.1% or something like that, or 0.16 instead of 0.165, right? But technically, that's what you do, use significant digits. But you wouldn't do it until you get to the very end, very last. Your calculations are all done. But in reality, you should, use a little bit of judgment and, just answer like in the same format. The other thing is, on the test, you guys constantly do this. We try and go back and look for it, examine every wrong answer on the exams or on the quizzes, but we're not infallible. We go back and look at it, and we're looking for stuff like you're answering, 0.14 instead of 14%, if we answer for percent, or, 14% instead of 0.14, and so on and so forth. We do go back and try and correct that, but, sometimes it falls so we don't notice it. So try and look at the format we're asking you for the question in. And particularly with these Blackboard things, because the Blackboard things, they use either a number range, or even more frequently, they use a matching. They're looking for matching digits. So in other words, they're looking for 0.14, for instance, right? Because that's what we asked for. We asked for in this 2 decimal places, 0.14. Okay, so if you answer 0.143, chances are mark you right, because it saw the pattern, right, to 0.14. But if you answered 0.1, you answered 0.15, and let's say it was let's say the answer is 0.149. If you answered, it searched for 0.149, but if you answered 0.15, it doesn't see the match, so it marked you wrong, right? So you got to be a little bit careful in answering the format that we're looking for. Okay, so let's do another one, and I want to do one that's a proportion. Okay, confidence interval. Okay, and by the way, guys, if I know you guys catch trains and stuff like that and have all sorts of other issues, and we got like a God only knows what's kind of bomb or cyclone or what they got going on today, right? I know that's happening. You don't have to worry about, especially the lab section. You don't have to worry about it because I'm recording it. You can always catch up with it later on. So if you need to, you can leave it out, letting me know. You don't have to announce it or warn me ahead of time or something like that, and I won't be offended. Okay, so I want to do a proportion now. And the way proportions work, I'm going to do one on the fly here rather than on this example. And the other thing I want to do before we call it a night is I want to show you how to do this in SPSS as well. Okay, so let's take a look at proportions. So how do proportions work? Well, let's say we take a poll, right? How many people use Facebook more than once? Check Facebook more than once a day? And we randomly survey the population we're interested in. Maybe we are interested in people between 20 and 25 years old in a certain income bracket, and that's our population, right? So, but I can't sample everybody because that population may be 20 million people. So I randomly do a phone survey. I sample, out of that population, I sample 1,000 people, right? And out of those 1,000 people, 150 of them tell me that they use that's a success, right? They tell me that they access Facebook, they check Facebook more than once a day, right? I'm guessing that like in that age range, probably more than that, right? Probably maybe 10 times a day or something. And so at any rate, so let's say it's 150. So what proportion of this population in our sample, what proportion of this sample actually access Facebook more than once a day? Well, it's 150 out of 1,000 people, right? So our proportion is equal to 150 over 1,000, which is equal to 0.15, 15% of our population. But this is a sample, right? We're not really interested in what the sample is. We're interested in that population of 20 million people. How many of them access Facebook more than once a day? So what we're really interested in is finding P for the population. But what I have is P, I'm going to call this because it's just like X bar, it's a point estimate, P cap. Represents, just like X bar represents the point estimate for the mean, this represents point estimate for the proportion. So our proportion is equal to 15%. Okay, so now in order to estimate how well I know this and calculate a confidence interval, I need to have a standard error. I have to have some idea what the spread would be in this kind of sample. So what's my standard error going to be equal to this time? It's a bit of a different calculation, right? It's equal to the square root of P times 1 minus P over the sample size, over N. Okay, so in this case, it's going to be equal to the square root of 0.15 times 0.85 over 1,000. Okay, and I'm going to get my calculator out and actually do this. Okay, clear 0.15 times 0.85 is equal to 0.1275 divided by 1,000. Comes up a pretty small number, and now I'm going to find the square root of it. The square root of that is equal to 0.00129. For our purposes, I'm going to round it to 0.1129. I could actually, in my calculator, put it into memory. That's my margin of error now. Actually, I'm going to do that. I'm going to put it into memory, plus memory. So now I can clear it, and it's still there. I can recall that number, right? Clear it again, right? So rather than round that number, I'm just going to store it so I can use it, right? So now I'm going to calculate my margin of error, my confidence interval. So what is it going to be equal to? It's going to be equal to P cap plus or minus 1.96 times my standard error, which I just calculated, right? So let's go back to my calculator. Okay, and I'm gonna recall that number. Okay, that's my standard error. This time I'm going to multiply it by 1.96. 1.96. Okay, and it comes out to 0.22. So I'm going to clear memory, and I'm going to put this in there now. So now I can take 0.15 and subtract my margin of error, minus, recall that, and it's 12 point, I'm going to call it 0.128. Okay, 0.128. And I'm going to add my margin of error to 0.15. Okay, I'm going to clear 0.15 plus my margin of error, which I'm going to recall, and that's equal to 17.172. 0.172. So I'm 95% confident that my true population proportion is between 12.8% and 17.2%. Right? What if I wanted a narrower range? What could I do to get a narrower range? Well, I want my standard error to be smaller, right? If I want a narrower range, I could increase my sample size. It would make my standard error smaller, right? So I could change my standard error, make it smaller by getting a bigger sample size. What about this number here? I can make that number smaller, right? I could make that number 1.64. But then I could only say that my confidence interval is what percentage? 90%. I could compromise and say I'm willing to be 90% sure, because I want a narrower range. If I want to be more certain, I would use 2.58, make it wider, and be 95% certain that I captured the true population proportion. So that's the way we would work with this. Now, where the hell does the t-score come in here? Okay, let's talk about the t-score. That's going to work both ways for, first, yes. Okay, let's do it in SPSS. Let's do I'm going to do a, proportions are a little bit sloppy in SPSS. You got to do a trick to use proportions, to do it for proportions in SPSS. However, I'm going to open up a data file, regular data file, and I'm going to take a sample from a population and calculate mean, standard deviation, and confidence interval. Okay, let's close that. Let's say open data. And I'm going to go to my desktop. And I'm going to go to data. And I'm going to try and remember which of these might have some. Okay, it's house selling prices. Let's see what that is. Okay, yes. I don't know what kind of data format you use. Okay, so here is a sample of house sales, and it looks like it's a sample size is 100. Oh, taxes, and this is say for some community we want to know what the average taxes people are paying. For instance, we randomly sample 100 homeowners, and we ask them how much taxes that they're paying. We want to know what the average is. So how would I do that? I go here to analyze descriptive statistics, descriptives, and I say I want to know what the average and standard deviation is for the taxes in this sample. And I'd say, okay, go ahead and calculate it for me. And it calculates it for me. It tells me that the average taxes paid is $1,668, and the standard deviation for the taxes, wow, a lot of variability there, is 1,009, right? A lot of variability in this. Okay, so now let's say that I want to know, what based on this sample, what is the 95% confidence interval for the average taxes? Well, instead of using analyze descriptive statistics descriptives, I'm going to go down to the next selection, which is explore. Okay, and explore, I can take my taxes, put it into my dependents list, and tell it, click on statistics. It's going to calculate, among other things, the descriptive statistics, and I can tell it here what confidence interval that I wanted to use. So I'm going to say 95%. I'm going to click continue. I'm going to say OK. And sure enough, it's going to come up and tell me that the average, just like before, was 1668. right? By my 95% confidence interval for the true population average taxes is 1462 to 1868. It actually does the calculation for you. Okay, now this is a large sample size, right? 100, relatively large sample size. What happens if we have a small sample size? If we have a small sample size, I'm going to go back to this, and close this, get a new piece of paper, and work real quick. So you guys, I was hoping to let you guys out of here early, but so much for that. Okay, so we'll just finish up with this because I do want to get some sort of t-test in here. And save. Okay, so now let's say that I don't know the population standard deviation. Let's say that I take a sample of size 16, and the mean for that sample is equal to 50. Now, I don't know sigma, so what am I going to use for standard deviation of the population? Well, the standard deviation of the population the standard deviation of the sample approximates the standard deviation of the sample, just like the mean approximates the mean of the sample, the x bar represents the mean of the sample. So I could take the standard deviation of my sample and use that instead of sigma. Okay, let's say that the standard deviation is equal to 12, right? Standard deviation is equal to 12. Well, I got a problem. And that is that when I do my confidence interval, x bar plus or minus my z-score, right, 1.96, times my standard error is going to be my confidence in 95% confidence interval. Well, the problem is that I can only use 1.96 if I'm using the normal distribution for the population standard deviation. I don't know what it is. So because I'm introducing extra uncertainty by using the standard deviation instead of sigma, I have to make up for that uncertainty. So I need to find, instead of using a z-score, I have to use a t-score. And that t-score is going to be based on what our confidence interval is going to be, still going to be 95%, but also on the size of the sample, or degrees of freedom. I'm going to write that in here, 0.95. I'm going to write in degrees of freedom instead of the sample sample size. The sample size was 16. I'm going to write in 15 here for degrees of freedom. Okay. Now I'm going to go to my t-table to find out what that t-value has to be. Okay. Let's see if I still got it here. I don't see it, so I'll look it up. Okay, come on. There it is. So I look it up for 95% confidence, and I go down here to 15 degrees of freedom, and instead of using 1.96 for that sample size, 16, in other words, 15 degrees of freedom, I have to use 2.131. So I go back here, and instead of using 1.96, I use 2.131. So my confidence interval is equal to 50 plus or minus 2.131 times my standard error. What was my standard error equal to? It's going to be equal to the standard deviation over the square root of the sample size, which is going to be 12 over 4 is equal to 3 times 3. So now I can add and subtract whatever this comes out to, 6 point something, from 50 to get my lower range confidence interval and my upper range of confidence interval. I do exactly the same thing, but because I don't know the population standard deviation, I have to use the t-score, which is always going to be a bigger number than 1.96 for a 95% confidence interval. It's always going to be a bigger number than 2.58 for a 99% confidence interval. And what's that number going to be? That number is going to be determined by the t-table, right? And notice something. As the sample size gets bigger, what happens to the t-score? Like here, sample size of 30, 2.04. Sample size of 50, 2.009. Sample size of 100, 1.98. What's it getting closer and closer to? 1.96, right? And an infinite sample size is 1.96. In other words, if you know the whole population, in other words, you know sigma, it's 1.96. So the t-score, you substitute based on the sample size. So if you have a very large sample, right, like 100, sample size of 100, a lot of statisticians will at least initially use just 1.96 because they say, hey, the t is going to be so close to 1.96 anyway, I'll just use this as an estimate. Okay, so sample size is important. In fact, in your textbook, it may suggest to you that rather than bothering to look up the t-score when the sample size is so big, then don't bother with that. Just go and use 1.96 instead, or 2.58, or so on and so forth. So that's where the t-score comes in. You substitute it for the z-score when you don't know the population standard deviation and you're working with a small sample. Otherwise, you do everything else the same. Okay? Call it a night.